Okay, so in this lecture, we're going to talk about another important concept in deep learning. That is autoencoders. So this comes around to some of the concepts we've talked about at the beginning of the course and at various stages, kind of talking about how the difference between supervised and unsupervised learning, which we've kind of explored in various ways throughout the course. And it kind of brings it all together because this is kind of dealing with that middle space. And in that middle space, there's a lot of advances being made recently that are proving to make deep learning very useful for all kinds of domains that were previously incredibly hard. So if you go back and remember, early on in the course I had various figures like this, and everyone has their own way of dividing up the fields of machine learning or data analysis, whatever you want to call these things. So this one comes from Kevin Murphy's textbook, which I was kind of using for the first part of the course. And it's kind of the classic way of dividing things up. So we have supervised learning methods, right? Where the main problems are classification and regression. And the idea is that you're given a label, right? And the label lets you train your model because you're basically trying to mimic what you were given. So building a mapping from your inputs to known outputs, right? You're building a function that fits the parameters that can produce those outputs, right? So that's well understood. And we talked a bit about some methods being unsupervised, whereas and we mentioned PCA and k-means as ways of basically not being given a label, but learning some kind of structure, either for clustering or for dimensionality reduction. So we're going to kind of update maybe what these terms here at the top, because what's important is how these are, the important parts that are real and everyone can agree on is here, what are the types of tasks that you have to do, right? In terms of these types of actual machine learning pattern recognition tasks, and there's the domains that they can be applied to. But this kind of terminology of what they have, as I kind of tried to indicate, there's a bunch of debate about it, right? And so we're going to continue that debate because there's been a lot of advances in this area of not having all the labels, or basically thinking you don't have any labels. And so it's changed the way people have thought about it a bit. Because we had semi-supervised learning, I talked about reinforcement learning a little bit, where essentially we don't have all the labels in different ways, and what do we call those? So I had a different figure which tried to group them by kind of algorithms, which is my own one. And what I'm going to do is kind of update this a little bit and say that, well, let's reevaluate what the words are for these. And it's not super important in a way because it's more important what you can use these algorithms for in terms of domain, but it's interesting to try to understand what they can be used for then and help us learn what's going forward. Because the main topic we're talking about today is this autoencoder. And like I said, it makes me think of this because it's classically been thought of as kind of unsupervised, and the more people do it and learn, it's like, oh, actually it's got a lot of supervision, it's just not from external labels, right? It's really this new thing which we're calling self-supervised. So I have a couple quotes here from Jan LeCun. I think it's from this, they had a long Facebook post about this at one point a couple years ago. There's a blog kind of article post, I'll connect. There we go, I've added the link. I had it on the later slide, so let's just put it in here. So these quotes are from kind of discussion you had on Twitter and Facebook amongst people about this topic, I guess a couple of years ago. But this post on Facebook's website has a nice summary of all those concepts, as well as connection to some new algorithms. So we'll go through a couple of things. So kind of reading these things recently kind of inspired me to rethink that this hierarchy. And so what we're talking about is that people talk about what unsupervised learning means, and talking about this other idea of self-supervised learning, where a model is taking data, using its input data as a way to learn about the structure of the problem, of the data domain, of the manifold, whatever you want to call it. Basically learn to understand the domain it's on by using its input data in a more rich way, right? So portions of the input are being used as a supervisory signal in order to build your predictor, your classifier, whatever. So we've talked about labels as, whether the data is labeled or unlabeled. But maybe a richer way to think about this is actually to say, what is the supervisory signal that your model is providing, right? And this is the thing that's going to be used to define the loss function, right? He went on to talk about how essentially you could think of what we call unsupervised learning and semi-supervised learning and even reinforcement learning as different types of self-supervised or partially supervised learning. So this is what I think is kind of interesting. If anyone asks you to define unsupervised learning and is kind of getting very picky about, oh, that's unsupervised and everyone knows that, and this is supervised and everyone knows that, it's like, well, yeah, LeCun thinks it's completely misleading to even call something unsupervised, because if it's not supervised at all, that means there's no data. What are we training it on, right? In a way, and I think we had questions about this earlier in some of the lectures, people questioning that idea, and it's true, right? Because no matter what you're fitting your model to, you have some assumption, some loss function, some pattern that you're maximizing, right? So PCA is unsupervised, right? But it is trying to optimize the dimensions for minimizing, for maximizing the amount of variation of the data explained per principal component, right, for these new dimensions. So this pattern in that data, and you've said we're going to look for this. We're going to focus on the variation of the data along these dimensions we don't know. Right? So you're using the data itself to find these new dimensions and then define that, right? So in a way, it's not unsupervised because you're reusing the totality of your data in a way that lets you extract a pattern, right? And so he's very excited about things, calling them self-supervised, because in some domains it becomes very useful, right? And so you guys should be able to think of another domain or another set of algorithms, really, that we did in this course that we could call self-supervised. Does one spring to mind? If I could see you, I'd look for your hands and try to pick someone. What about, word2vec and glove, right? Our text processing stuff for natural language, right? That was very self-supervised, right? So look at my new table here, which is also just another interpretation of how to understand these terms and whether they're useful. So take it with a grain of salt and just help you try to understand how they fit together. But using some of these things people are talking about more recently about unsupervised and supervised learning. So we know what supervised learning is, right? We're given some signal, which we've always called the labels, right? And they're provided by us, the user, or the modeler, or some kind of environment, but it's external, right? And these are our favorite classic methods of just logistic regression, support vector machines, random forests, I guess k-nearest neighbors, and everything we've talked about for deep learning so far is being done with supervised learning here as well, right? So even when we talk about semi-supervised at the beginning, I kind of question, well, what does that really mean? It just means you have some of your data. Oops, I didn't finish the sentence there. Some labels available, right? But again, they have to come from us, and we say that, you know, maybe it can deal with partial missing information or something like that. But it's not that well defined either, in a way. So reinforcement learning as a domain, in a way, uses even less supervision because it has to interact with the environment and get this feedback signal. And that's the thing that in that domain we call the reward. So it's even actually more sparse than labels. So that was an interesting one for me to think about. That's a different way of seeing it. And then unsupervised learning, which we assume we knew what it meant, was like PCA, and we had clustering methods, right? We said k-means and other methods for clustering. Are they really unsupervised? As we're questioning. I already talked about how maybe PCA can be said to be using some kind of information about the data, right? In k-means in dbScan, you also have some assumptions, right, about the distribution of the data or the relationship, so that, you know, in k-means we assume, right, that similar points are near each other in the space, and so we're taking advantage of the locality in space to extract this pattern. And in dbScan, we're making assumptions about the density of the data near each other, in that if they have a certain density pattern, right, with the inliers and outliers of those different types of neighbors, then we call them to be in the same group, right? But we're essentially allowed to mine back and forth over the entire data set to extract these. So it's unsupervised in the sense that no reward is coming in, no label is coming in, but we're allowed to use that. So why we're thinking about it this way is that these other methods, which are also supposed to be unsupervised, definitely use the data explicitly, right? So we're talking about autoencoders, and these more naturally get thought of as self-supervised, right? And so we talked about Word2Vec and Glove. I forgot to write that in there earlier in the course, right, where we've got a sequence of words, and we're looking for relationships between adjacent words and relationships between numbers of certain words in documents, and we're definitely using the data, the input data itself, as the signal that we're going to use to learn our model, right? So now we've got a new one, Autoencoder, that does that, but uses deep learning. So what is that all about? So what is an autoencoder? So an autoencoder is a network, a neural network, that takes some input X and tries to reconstruct it, basically produce as the output of its network the same input that was given to it. So it's reconstruction. R is what the output is, and your loss function will be defined using the error of how well you reconstruct the input, right? So if you have a perfect reconstruction and R is equal to X exactly, then the network's perfect and you don't need to do any more training, right? So this might sound like a really dumb idea. Why are we trying to build a network to just reproduce something we already have? Because we have X, why do we need to build something complicated and train it just to reproduce that, right? But there's a reason. We're not doing this for the reconstruction. We're doing this for the magic sauce inside the network. So people often complain about deep learning, that they're black boxes, right? That you've got some input and some magic kind of function inside with a whole bunch of parameters, and then it produces some output and you can't really tell what's going on, right? So we showed a little bit in the CNN lecture last week that you can do some interpretation, at least when they're visual. So there's some hope that you can try to tease apart what's going on what's going on inside a neural network. But you can't always do that. But in this case, we're explicitly basically trying to build these black boxes because we want the black box. Not because we're going to understand it and read it out or interpret it, but just so we can reuse it, right? So the idea is that you want to train an autoencoder to get this H, right? You want this hidden layer, you want this function that turns your data into some hidden encoding, and then some other function, G, that turns your hidden encoding into an output, and that output's a pretty good reconstruction of the input. But that means hopefully you could do it for other data. But it also means that this H hidden representation and these functions somehow understand the data in a fairly complex way. That's the hope. So you can treat these functions as probability distributions, and say, that we're basically trying to come up with the most likely encoding, representation in the center here of whatever, how many weights this is in the center of the network, to explain this input data and this output data, knowing that they should be interchangeable. And so H is a way of representing the data X that you were giving it, right? It's a representation or an encoding of it. So again, this will only seem useful once you start realizing what you can use the encoding for. Like, what is an encoding? So there's different ways you could construct this. So if I switch to my whiteboard, right, let's say we have our input X. Oops. We have our input data X, which is being fed in, and this could be numbers or images. Let's assume initially that's just numbers. And then we're going to have some network that can take these as inputs, right? And we're, I'll just leave that. We said we're going to have a hidden layer. Now we could have multiple hidden layers. So we'll say this is, just H1, but it could be H1, H2, H3 with hidden things inside. But let's just say it's represented as one thing right now, because it doesn't really matter. You have some number of layers here, right? And as usual, we're talking about a fully connected thing, so every one of these hidden nodes is taking data from all the ones from the previous layer, and then we're trying to produce some output. Now the output has to be the same dimensionality as the input, so we're going to have the same number of them. So somehow we want to get from there to here, right? But I guess the question is then here is how many nodes do you want to have in these middle layers, right? How many depth, but also how thick, right? And so if we talk about it being smaller, then you could start seeing why it might be interesting, right? So if we had X having X is in like 100 dimensional space, and then H is just in like 5, our Y obviously has to be the same as our input. That's just 100. Now how does this encoding, how can it represent something so complex? The 100-dimensional data in just 5 dimensions, right? That's the whole question. And can you do that? So if you can, then this 5-dimensional kind of representation, H, is going to be something that is much more compact, right, than what you had initially. So this should sound familiar to you as well. If you think about what we did with manifold learning and dimensionality reduction, you're essentially learning lower dimensional representations of your data and trying to have something that generalizes better, where simple differences between data points might be representative of a more complex relationship in the original space. But now we're generalizing this in a very broad way by just saying there's a neural network, and it just does this because it has a smaller number of layers in the middle. Right, so we want the functions that are building this autoencoder to have low capacity, so they have to basically learn as much as possible about the data, right? So in a special case where we say that the loss function for this whole neural network, and this represents those two hidden layers, so essentially this is the whole network. What we're optimizing is just the mean squared error. So like as I was saying, like your reconstruction of your data. So you just say, what's the mean squared error between every data point being exactly similar to the input? If we have linear functions, so if we got rid of the nonlinearity in our neural network, right? So no ReLU or sigmoid. We're just using a sum. Then we end up getting PCA, essentially, right? Because we'd be learning something that kind of optimizes for that, and mean squared error is kind of capturing this kind of variation concept. And so we're learning a new lower dimensional subspace that gives us the eigenvectors. You had like just a single layer in the middle, right? Right, so it's very similar to that idea of manifold learning and dimensionality reduction, but now we've generalized it to be something where we could have a number of hidden layers and have this kind of be richer, and maybe then a common thing, as we'll show, I guess, in another slide, will be that you have your input data of some size, right, and then we're going to have a number of hidden layers, and it's going to have a much smaller number, right? And so you can basically do any architecture you want like this, where you're just changing the sizes. And again, these are all fully connected every time. And so now the encoding you want is going to be this, and this can be very compact, right? You don't want to be so small that you can't fit it, but then you'll know that by how well you do at this problem of computing the error between x and y in some way, right? And this doesn't have to be error exactly, but this is our goal, right? We want this encoding in some way so that we can use it for other things, just like we would where we have dimensionality reduction. We want to have something that's smaller, so similarities of those vectors. So for every different input that we get of our data, we can basically, once we've learned this, we can use this encoding for any data input we get, even one we haven't seen before, and use this vector as the string that represents it, right? And we can do similarity measures, so distance between encodings of words, and see if they're similar or not, right? To figure out if a data point is an outlier or normal, or which class it belongs to. These encodings can be used for many things. You also could have a neural network where the hidden layer has more nodes than the data. This is not generally done, as far as I see. This is very possible for it to overfit too much, because it's got a lot of weights, and it's not really giving you something more compact. It's not clear what it's doing, but it will work as well, right? And you definitely have to kind of regularize it in a strong way, so that you're trying to encourage it to find something useful. But the usual idea is that we're talking about undercomplete autoencoders, where the hidden layer has a smaller capacity, lower dimensionality than the data itself. We still have to be careful not to have them overfit, but that's why you want this hidden layer to be kind of quite a bit smaller than the dimensionality of the data. So with that concept, you've got a lot of different things you can do. This basic autoencoder is what I'm talking about here. And yeah, so I mean, for this discussion connected with the textbook, this chapter 14 of the deep learning textbook relates to this. So they have other kind of various details about it. But in a way, it's not really different than training a normal neural network, because once you have the output label for every data point input data, you have the known output label, and that's what Jan LeCun was talking about. Essentially, you have a lot of training data, because every data point has its own data, right? but you still do backpropagation as usual, and try to update that, optimize that network for that data set. So there's some other other regularization properties we have to kind of enforce in order to try to get them to not overfit too much, right? So regularization is very important for a bunch of these different types of autoencoders. Sparse autoencoders, you might have the hidden layer have a higher dimensionality than the data, like we were saying, but you have to be very careful to heavily regularize it, adding penalties to basically enforce it to have a simple representation. So maybe you're looking for, a high, it can have more dimensions than the data, but you want a binary representation of your data, right? And so you can say, well, it has to be binary, or it has to even be like a one hot encoding or something, or a few hot encoding, so that you really should only have a small number of bits in here that are meaningful and the rest are zeros. And so it's trying to find a kind of weak classifier of all the different data points using this representation. So then in that space, distances would be very clear and related to classification. But you can do that by basically coming up with some kind of penalization code. And it could just be the sum of the encoder, because the hidden layer, the encoding, is just a bunch of numbers, right? So you can say what's the sum of that and have the squared sum of that. And so you have an L2 regularizer that you add to the cost function, trying to minimize the log loss. And so you add this L2 norm term by summing up the embedding, and so it'll try to get that to be as small as possible, but still satisfy the reconstruction goal, right? That's one way. Contractive autoencoders they instead add the penalization term to the weights, to the gradient itself. To the gradient. And make it so that you're not updating the weights too aggressively. This is similar to changing the step size, right? Where we're talking about slowly reducing the step size, so you take smaller and smaller steps over time. You can add penalization term to the gradient to say if the gradient's too large, then you kind of you weight it down so you don't just follow it so much. So the larger the gradients are, or the more they're all in one direction, you kind of have an inversely proportional penalty that kind of tamps it down a bit, so you don't just go off in wild directions. That's another thing people use. Variational autoencoders, we have a separate lecture on that, so you can go look on YouTube and look at the next lecture here. But what I'm going to talk about here a bit is denoising autoencoders, which is a particular kind of subset of this, and it's kind of related to a lot of the things that are happening in text processing, to follow up on things we did with Word2Vec.